Welcome to another edition of 3D Printing News Unpeeled, live with yours Peels, courtesy of 3dprint.com. Join me as we look through the important 3D printing news of today. So today we're going to start with ASML. So ASML is a company that makes, well, probably the most demanding and most complex and exacting machine that this earth has to offer. ASML is a Dutch company, and they make lithography machines for making integrated circuits, chips. And these machines, as you can see in front of you, are very, very complex indeed. And indeed, in order to make them, ASML needs to make many machines that make other machines that make parts. And the parts have to be of an unimaginable accuracy. The ASML is usually quite a secretive place, and it's nice that they've disclosed that they make over 200 3D printed parts for their EUV machine, their extreme ultraviolet machine, which is currently the leading cutting edge platform for producing chips that are in all the latest devices. The rationale for ASML for using 3D printing is first off, they can't produce quick enough. Some components just have longer lead times, and they really need to ramp up production. ASML is a very cyclical business. If there's a lot of electronics on demand, then companies want to invest and build fabs, these large facilities that can produce these chips, and they want to get the fabs very, very quickly out the door, and they want to get the chips out the door very quickly. If the economy, or specifically the electronics business, is doing badly, then ASML is going to sell very few machines. Just geometry optimization for very specific things is also very important to ASML, and something very, well, maybe not peculiar to them, but very important to them in particular, is to validate assembly processes and to try to see if things can be manufactured in the right way. They make parts of the machine's wafer and reticle stages. One example part is a part where that you see in front of you. That is essentially, it's for the wafer table. It's got fluid. It's kind of fluid power, kind of a solution where for carrying the wafer table. Now this needs to be extremely accurate. And I'm seeing the motion control on this wafer table, that is actual wafer that's being produced, and then later to go on to become a bunch of chips. It needs to be very accurate in terms of the positioning accuracy, and this needs to be a very reliable, repeatable process. So what they used to have is a massive block of PEEK, which you can see on the left side in the engineering drawing, and they bored holes in it to let the fluid through. And on the right is the powder bed fusion and metal component for improving the watering of this carrying table. Now, what they optimized for, you can see some weight loss stuff going on here. And of course, they optimize for flow through the component, just like other people make kind of hydraulics and other kind of fluid power kind of components. But what specifically is really important to ASML is turbulence. And this part on the left was causing turbulence. So what we see right now is that the optimized part caused 10 times less turbulence. Now, for ASML, any kind of improvement in accuracy, any kind of improvement in process control, any kind of elimination of some kind of distortion is huge. So this already makes it very worthwhile. They're also interested in making like things apart from just liquid transport, just things like thermal control. They're using, besides powder bed fusion for metal, which is the most that they used, they also use powder bed fusion for polymer, mainly using polyamide. They also use FDM for PEEK and also polycarbonate. And they also inkjet ceramics, which is a bit more noble. What they do with like the polyamide sintered parts, they use them for vacuum components, vacuum assembly components, like tubes and things like that. They also like to use the FDM parts because there's no off-gassing on the PEEK and polycarbonate parts. That's important for them, of course. And one of the first parts they've 3D printed were actually a FDM part, a material extrusion part in PEEK, which was a track for optics to go along. And that they printed back in 2008. So ASML has been doing a considerable bit for a considerable amount of time. What they do now is the component you see in front of you is as well. This is kind of a PC wire guide, a polycarbonate wire guard, which they use as well. So I think this is a really interesting use, and I think the really thing to learn here is that a company like this, ASML is a 21 billion revenue company, so they have a lot of resources. You can really implement AM to do really specific things for them, for whatever is key to outperforming others for them. Like this turbulence thing, we don't really think of designing for turbulence, right? Or turbulence in any kind of in a motion unit. But of course, for them, it's very important. So I think not a lot of people are taking advantage of what additive really has to offer, is to just develop a part or device exactly how you need it to be. And this extreme example of what ASML is doing is, I think, indicative of what we could do going forward in a lot of different applications as well. The next thing is, well, it involves a very familiar name, Joseph DeSimone, who you may remember. You probably remember him as he's a college professor who invented, one of the inventors of CLIP, carbon technology. It used to be carbon CO. He is not anymore, but he certainly hasn't been kicking back on the beach somewhere. What he's been doing is, along with a group of people at Stanford, they published some research in Science Advances of a process that they believe is maybe 5 to 10 times faster than some existing processes, which we'll of course have to verify if that's true or not. This process is called iCLIP. So iCLIP solves a particular problem that carbon's clip technology has, and other things, is if we raise an object in the fluid bath, the resin is basically pulled up alongside the object. This limits the speed at which you can extract an object. And in particular for carbon technology, it could limit the cross section of this object, and also the size of the object, kind of. So iCLIP, what it does is it builds tubes, right? As the part is built, tubes are being built, and these tubes allow for additional material to be injected to them, and then at a local part to aid the speed at which the object can be pulled up out of the bath. So that could be very exciting, just out of a speed kind of a thing, just hey, it's faster, right? That could be good. But on top of that, what is also possible is to then inject different materials, so different photocurable materials, at a very localized state. The picture in front of you is of St. Sophia Cathedral in Ukraine, and they tried to mix several different materials. Now, as you can see, it's all rather crude at the moment. But by taking more viscous materials, right, than what they can normally build with, they could maybe have different properties, or they can have different properties at different parts. And ultimately, obviously, what they want is kind of a functioning graded part kind of thing, using this iCLIP or injection clip technology, where they can use the best qualities of just some regular build material, let's say, and an injectable material with different properties at certain precise locations. Now, this is a very promising technology. It's interesting to see a refinement. I mean, we always see people either trying to create their own IP stack, or we see people just trying to make a bog standard printer that everyone else uses. And this is definitely a refinement of an existing technology, and that is something we can only applaud. What is the impact of this? We'll see. They might allow them to use different materials and really extend the life and functionality of that kind of a technology. So that could be, it could be interesting. I'm not sure yet. Early they tell, but it's really nice that this is happening at Stanford, that people are doing this kind of stuff. The next thing I'm a huge fan of, this is what you see in front of you, is a 2-cent euro coin. On the right is a MEMS device. So MEMS, as you know, are little tiny machines that are all over your iPhone or your Fitbit or all sorts of electronic devices. These are made in their millions, and they're small electromechanical devices that can be used, for example, as a pressure sensor or as accelerometer. They're the things that tell your phone that you're walking, that kind of thing. Now, MEMS are really very special devices, and they're really good at what they do. But the problem is the spin-up cost, or the cost it takes to get a new MEMS sensor or kind of other device underway is considerable. So they're only really, for an accelerator for all the phones in the world, it really makes sense to do MEMS. But a lot of other low volume stuff, MEMS is not really that exciting. So I wrote, it's really cool actually, because I wrote a story about something like this, using 3D printing to make low volume MEMS a couple of weeks ago. And this is something that apparently some people are already working on. The people that are working on this is Frank Niklaus. And Frank Niklaus is at the KTH Royal Institute of Technology in Stockholm. In a paper published in Nature Microsystems and Nanoengineering, they're looking at cost effectively producing short-run kind of MEMS-like MEMS devices. So what they're doing is they're saying, look, we can now find a new technology, and that new technology, or the new kind of production method can make then MEMS in really small, with really low startup costs and in really small numbers. So we can make 1,000 MEMS for like a particular sensor. For imagine you're making like a kind of particular sensor for a prosthetic. You know you're only going to sell 1,000 of them, right? But the traditional MEMS sensors don't work for you, right? Well, then the pressure, so you could develop a pressure sensor that's specifically for this to make your finger of your prosthetic device work a little bit better, for example. So you can make a MEMS that really helps you touch and ground things better. And that, of course, such applications, or the enablement of such applications, could be huge. That's why this is by far the #1 news item for the day. This has an incredible impact, not only because of Frank Nicklaus's work and his team, of course, but also because of all the other stuff that if people are inspired by this, lots of other people are going to find out ways of making similar things happen. So it's about the thinking inside this new kind of sandbox has been created that can really let people think in a fundamentally new way about how to solve problems and how to solve like really kind of like really remote or really unsolvable problems right now, because it just costs too much to make a MEMS device. So smaller volume manufacturing is really, really very key. Now, how are they doing this? They're doing 2PP or two-photon polymerization, and they're combining it with something called shadow masking, where they're essentially, it's like kind of like a stencil, where they put the conductive material, they drop the conductive material over part of the model that's covered and then part of the model that isn't, making certain parts conductive, insulating or not. And the combination of these technologies allows them to, in a few hours, make MEMS accelerometers. That's what they've demonstrated so far on the paper. And they could do a few thousand of these a year. So again, low volume applications, very specific devices, but really low cost to get started, and a development cost that would be much easier than what other people are used to, right? Much easier, much faster. They're essentially democratizing MEMS, if you will. And I think this is a fantastic development. I think this is something that I theorized this a couple of weeks ago in the story, and I didn't think that someone would be already working on it and already be so close to coming up with a solution that could really change a lot of things and really change how a lot of devices are developed. Think of IoT sensors for your devices and for sensors and that you want on next generation devices that are working completely differently. Ways to differentiate through having the different sensors on your phone or your other kind of small volume electronic device. So this is, I think, a really fundamental breakthrough. We have yet to see, of course, if more people are going to adopt this technology and if it's going to make it to market in any meaningful way. But if enough people get inspired by this work, I think it could be quite a considerable, quite a impactful development. So thank you so much today for joining me for this edition of 3D Printing News Unpeeled, or Additive Manufacturing News Unpeeled. Thanks to 3dprint.com, of course. And yeah, and hope you enjoyed it and have a great weekend. Have a great time. Thank you.